A very good morning, students. So today we are going to start fourth unit. So in that fourth unit, we are going to discuss Z transform. So what does mean by Z transform? So in previous unit we discussed Laplace transform and Fourier transform. So what's the difference between Laplace transform and Fourier transform? So in that Laplace transform we have ROC, and in the case of Fourier transform we don't have ROC. That is the main difference between Fourier transform and Laplace transform. Both are analog case only. But in in discrete transform, so there is a tool which is used to transform the analog into discrete. That is mainly used for discrete case. So how to represent the discrete signal means x of n. So in that discrete signal we can perform using Z transform tool. Okay. So understanding the relationship between transform and Fourier transform for discrete time signals, and understanding the characteristics and properties of Z transform, and ability to compute Z transform and inverse Z transform, ability to apply Z transform for analyzing linear time invariant system, and definition. So the Z transform of x of n is denoted by x of z, which is defined as, so x of z which is equal to summation n which is equal to minus infinity to plus infinity x of n into z power minus n, where z is a continuous complex variable. So in that complex variable means we have a real and imaginary part, and we have a magnitude part means root of a square plus b, that is real square plus imaginary squared, and phase angle means that is tan inverse of b by a, that is imaginary term divided by real term. And the relation with Fourier transform, see we consider the continuous time sampled signal x of t with the sampling interval of t from x of n. So here s of t which is equal to summation n which is equal to minus infinity to plus infinity, and x of n is del of t minus nt. And taking Fourier transform s of t with using properties of del of t, and xs of j omega which is equal to minus infinity plus infinity x s of t into e power minus j omega t into dt. So which is nothing but minus infinity plus infinity and a summation n which is equal to minus infinity plus infinity x of n into del of t minus nt into e power minus j omega t into dt. So which is equal to summation n which is equal to minus infinity plus infinity modulus of x of n into e power minus j omega nt, and defining omega which is equal to omega t as the discrete time frequency parameter, and writing x s of j omega as x e of j omega. So it becomes x e of j omega which is equal to summation n which is equal to minus infinity plus infinity x of n into e power minus j omega n. So which is known as discrete time Fourier transform, that is DTFT, or Fourier transform of discrete time signal. Is it clear? And x e of j omega is periodic with period 2 pi. So in first unit we have studied periodic signal and aperiodic signal. If the signal is periodic one means if the time period is periodic one, and if the period is non-periodic signal is nothing but is a rational one. And x e of j omega is periodic with period 2 pi x e of j omega which is equal to summation n which is equal to minus infinity plus infinity x of n into e power minus j omega n, and which is equal to summation n which is equal to minus infinity plus infinity x of n into e power minus j omega plus 2 into k pi n divided by n, where x which is equal to e of j omega plus 2 k pi, where k is an integer. Since z is a continuous complex variable, we can write where r which is equal to modulus of z greater than 0 is magnitude, and omega which is equal to phase angle of z. This is a real part, and imaginary part is angle of employing the z transform as x of z which is equal to x into r into e power j omega, which is equal to x of r into e power j omega, which is equal to summation n which is equal to minus infinity plus infinity x of n into r power minus n into e power minus j omega n, and which is equal to the dft of x of n into r power minus n, where r which is equal to 1 or z which is equal to e power j omega, so where identical. And this is a relationship between x of z and x of e power j omega on the z plane. So here instead of x of z, we have to substitute e power j omega. X of z where z which is equal to e power j omega means x of e power j omega which is equal to summation n which is equal to minus infinity plus infinity modulus of x of n into e power minus j omega n. So here we have a unit circle, that is modulus of z which is equal to r which is equal to 1. So that is real term and imaginary term. We have a phase angle omega, and in z plane we have to substitute real and imaginary part. That is z which is equal to e power j omega, and pi which is equal to minus tan inverse of b by a. So this is the relation between x of z transform and discrete time Fourier transform. And region of convergence. So what does mean by region of convergence? ROC is region of we already studied in Laplace transform itself. So region of convergence indicates when Z transform of a sequence converge, generally there exists some Z such that modulus of x which is equal to modulus of n which is equal to minus infinity plus infinity, x of n into z power minus n which lies between, which tends to infinity. So where z transform does not converge, the set of values of z for which x of z converge are modulus of x of z which is equal to modulus of summation n which is equal to minus infinity plus infinity x of n which is equal to z power minus n and less than or equal to summation n which is equal to minus infinity plus infinity and modulus of x of n z power minus n less than infinity. So that is called a ROC, which must be specified along with x of z in order to for the z transform to be complete. And assuming that modulus of x of n is a finite, that is infinite length, so we decompose x of z. So that is x of z we have a positive and negative term which can be represented by x of z which is equal to x of minus z plus x of plus z. So where x of minus z which is equal to n which is equal to minus infinity to minus 1, x of n into z power minus n which is equal to summation n m which is equal to 1 to infinity x of minus m into z power m, and x plus of z which is equal to summation n which is equal to 0 to infinity x of n into z power minus n. Let f n of z which is equal to x of n into z power minus n, where x plus of z is expand as x plus z which is equal to x of 0 into z power minus 0 plus x of 1 into z power 1 plus up to x of n into z power minus n, which is equal to f of 0 z plus f of 1 into z plus f of fn of z. That is f of z is nothing but x of z. So that is x of z and x1 of z plus up to x1 of z. So here we have a x1 of z power minus n plus x2 of z power minus n, like that it will extend up to x of n into z power minus n. And according to the ratio test coverage of x plus of z requires a limit n tends to infinity f n plus 1 of z divided by f n of z less than 1. So let limit n tends to infinity where x n of plus 1 x of n which is equal to or plus less than greater than 0 x plus of z converge if, and limit n tends to infinity, that is modulus of x of n plus 1 into z power minus n minus 1 divided by x of n into z power minus n which is equal to limit n tends to infinity x of n plus 1 divided by x of n into z power minus 1 less than 1. So modulus of z greater than limit n tends to infinity and x of n plus 1 divided by x of n which is equal to r. That is the ROC for x plus of z is modulus of z greater than r. And thank you students. The remaining part will discuss next class.